You're really quiet, just FYI. Hello, world. This is CS50. My name is David Malan.
I'm Brian Yu.
And we're here for a live stream of CS50's new course on fundamentals of artificial intelligence, led by CS50's own Brian Yu. This is very much a behind-the-scenes live stream wherein we will likely start and stop a bunch of times to make corrections, make fixes. The course itself, as well as its assignments and more, will be on edX and YouTube and elsewhere later this year. Brian, what do we have in store for today, then?
Yeah, today, so we're taking a look at some of the fundamentals of artificial intelligence. Today is going to be all about analyzing data, in particular focusing on unsupervised machine learning. So that's what we'll be looking at today.
All right, if you have any questions during, I will be on the chat and back, so feel free to verbalize them there. I'll do my best to relay some of them by raising my hand to Brian or try to intercept them myself via chat. This is CS50.
Thanks, everyone. Ready to go. Oh, OK, great. Thanks. Welcome back, everyone, to Fundamentals of Artificial Intelligence. So last time we were taking a look at how we can give an AI some data, have the AI learn some patterns in that data, and then use that information in order to make predictions. One of the examples we looked at last time had to do with sorry, actually, let me start over. Welcome back, everyone, to Fundamentals of Artificial Intelligence. So last time we were taking a look at strategies we can use to give the AI some data, have the AI learn some patterns in that data, and then use what it learned in order to make some predictions. And today we're going to continue that line of thinking, exploring how we can use AI to analyze data in even more different kinds of ways. So last time, we looked at data kind of like this. There was a data set of flowers that we had access to, where we had information about different features related to those flowers. And then at the end, we were trying to predict a class, meaning which category did that data belong to? Was it one variety of flower, or was it some other variety of flower? And this class here at the bottom of our data set is what we call a label. It's a label describing what this part of the data belongs to. This data belongs to class 1. That data over there belongs to class 0. And in general, whenever we're using AI to analyze data of this form, labeled data where there's some label we're trying to predict, we call that supervised learning. There's some label, meaning it's raining or it's not raining, it's this flower or it's that flower, and that is the label that we're trying to get the AI to learn. But sometimes we're working with data, and that data doesn't always have labels, and we might still want our AI to be able to make some decisions about it, to be able to reason about it, and find some patterns. Then we call that unsupervised learning. And that's going to be the focus of today, exploring how we can give AI some unlabeled data and figure out how the AI can still make sense of it. So instead of having data where we're going to have a particular class that we're trying to predict, that class is no longer going to be there. We're going to have some data, just unstructured. It might have a bunch of different variables, but we're going to try and figure out what kinds of analysis, what kinds of patterns we can figure out based on that data that we already have. So what are the potential applications of unsupervised machine learning? Well, one of the most common is clustering, taking a bunch of data and trying to organize it into different groups and to figure out what groups they belong to. And clustering comes up all the time. If you are running a website and have a bunch of users, you might want to group your users into different categories based on which users are similar to other users. If you have a bunch of documents, be they posts on social media or emails, you might want to figure out how you can organize those and find groups of emails that are similar to each other too. So lots of different ways that we might imagine clustering. And let's take a look at an example. So here we have a bunch of different points of data all organized together. And let me first ask you, before we think about how an algorithm might understand it, how might you think about organizing this data into clusters? And if you're like me, you probably notice that there are some regions of points of data here that seem to be similar to each other. There are a bunch of points down here that appear to be similar to each other. Maybe there's a cluster up here on top, and there seems to be a cluster over there in the lower right of just points of data that appear to be in a group together. And what we'd like to do is give a computer data like this and have the computer figure out for itself what the three clusters are. So how could we do this? Initially, the computer doesn't know where the three clusters might be. But as with other examples of AI that we've seen before, we've seen that we can often start with an AI that's not very good at something and iteratively improve it step by step. We saw that last time with neural networks, where we started with a neural network that wasn't very good at making a prediction, but over time, we were able to iteratively improve it, adjusting the weights in order to make that neural network better at making certain kinds of predictions. And we'll try that same idea here when trying to figure out where these clusters are. If we don't know what the three clusters are, let's just start by guessing randomly. I'm going to plot these. So these are what the clusters we think we want to eventually end up with are. But how would we get the computer to figure this out? I'm going to start by plotting three what we call cluster centroids, which are going to be the centers of our new clusters. There's one red one here, a green one there, and a blue one over there. And right now, they're just random. I've randomly selected three locations in this space for where those clusters might be. And now what we'd like to do is assign each one of these circular points to one of these clusters, either the red cluster or the green cluster or the blue cluster. And if we just assign each point to its nearest cluster, this is what we end up with. We end up with a red cluster, which is all of these points. These are the points that are closest to the red cluster centroid over here. Then we have a green cluster right here. These are all of the points that are closest to the green cluster centroid. And then over on the right side, we have one third and final cluster. These blue points, those are the ones that, of the three cluster centroids, right now they're closest to the blue one. Now this didn't quite match our intuition for what we thought the clusters would be. We thought these should all be one cluster. We thought these should all be one cluster. So this doesn't quite line up, but we can figure out now how we can iteratively improve on this current clustering that we have demonstrated visually here. And one thing we might do is to say that these cluster centroids, these plus symbols, the red, green, and blue one, ideally those should be at the middle of the cluster. But right now they're not at the middle of the cluster. They're just randomly located. So I'm going to move each of these cluster centroids to the middle of the points that are currently in that cluster. So the red centroid is going to move to the center of all of the points that are currently red. The green one is going to move to the center of the ones that are green. Same for the blue one, where we're just taking all of the points that currently belong to that cluster, averaging their positions together, and then updating the cluster centroid to represent the middle of that new cluster. So we've made a little bit of change, but now what you might notice is because we've moved where the cluster centroids are, now some of the points that used to be closer to one color might now be closer to a different color. And I'll highlight those for you now. That these 2 points that used to be closest to the green cluster centroid, well, now they're actually closer to the red cluster centroid. And the same can be said of this point over here that used to be closest to the blue centroid. Now it really seems to be closer to being part of the green cluster instead. So any points that have now shifted in terms of which cluster they're now closest to, we can reassign their colors. These 2 greens are going to become a red. That one that used to be blue is now going to be a green. And now we can repeat the process. We'll go ahead and take each of these cluster centroids and update their position to be the new average of all of the positions of the points that were in that cluster. And we repeat the process again. Are there any points now that used to belong to one cluster that now we want to reassign to a different cluster? And we can see that now that's true for a couple of points. This one up here that used to be closest to the red centroid, now that the blue centroid is starting to move up a little bit, this one's now actually closest to the blue one. And these 2 points over here, again, because the green centroid has now been moving closer to it, these now, instead of belonging to blue, those are going to belong to green instead. So we can reassign what clusters those belong to and repeat the process again. Now that's true for a few more. These 2 that used to be closest to red are now closest to blue. That one that used to be closest to blue now actually is closer to green. So we'll update one more time, and we'll repeat the process. We'll do it again. These 2 are now definitely closer to blue than they are to red, so we'll update those to be blue, update the positions of the clusters, and we'll do it one last time. These 2 that used to be closest to red now again are closer to blue. And at this point, we can check and see, do any of them need to be reassigned again? But in this case, they don't. Every point is now closest to the cluster centroid that it was closest to in the round before. And at that point, we can say we've reached convergence. That's a common idea that we'll see when we're dealing with artificial intelligence algorithms, the idea that we can repeat a process again and again, making small changes until there are no more changes left to make. And once there are no more changes left to make, we know we've reached something that, at least for now, we can't seem to improve on any further. And it does now seem that what this algorithm has arrived at, by starting with just completely random decisions for where we wanted the clusters to be, we now have 3 clusters that seem to be about right. They sort of match our intuition. For we have one cluster over here, a second cluster here, and then a third cluster over there in the lower right. And so this algorithm that we've just followed is called k-means clustering, where k is the number that we get to choose. We choose how many clusters do we want to organize our data into. In this case, we chose k equals 3 for 3 clusters. And essentially, we're deciding to cluster them by choosing random positions for the clusters and then iteratively updating their position, making them the mean or the average of all of the points that they're nearest to, and then updating what clusters each point belongs to based on which of the cluster centers they appear to be closest to in each round. And so k-means clustering is a pretty popular technique for being able to take a bunch of data and figure out what clusters they belong to. Now, there are some things we have to take into consideration with this algorithm. One was, you might have noticed that I, the person programming this algorithm, I, the person doing this clustering, needed to decide what the value of k was. I said, looking at it visually, that I wanted there to be 3 clusters. And so the first step of the algorithm was to pick 3 cluster centroids at random somewhere in space. But I didn't have to pick 3. I could have picked a different number instead. And so say, for example, I chose to pick 4 cluster centroids instead of 3. Now I'd start with randomly choosing 4 different locations. I would assign each of the points to whichever of the 4, red, blue, green, or yellow, they happen to be closest to. And let's go ahead and run through this algorithm and see what happens if I apply k-means clustering, this time with 4 cluster centroids instead of 3. We'll go ahead and we see our 4 clusters. We have the red one here, we have the blue one over there, we have the green cluster over here, and then the yellow cluster over on the right. And if we apply this algorithm, we'll move the cluster centroids to the center of all of the points that are currently in that cluster. Then we'll update any of the ones whose clusters have now changed. Some of the reds are going to change to be either green or yellow. We'll update again, keep repeating this process, and now repeat again. And one more time, this blue one here used to become blue, but now it seems to be closer to red. We'll update it to red. And at this point, we will have reached convergence. The centers have moved, and there's no more points that need to switch into a different cluster. And we have 4 clusters. And it's kind of up to us now to decide if this is more useful than the 3 clusters we had before. Maybe we do want to take this cluster down here that used to be 1 cluster and divide it into 2 sections. Maybe we want to think of these points as different from those points over there. But that's a decision we're going to have to make in terms of figuring out what the appropriate number of clusters is. Yeah?
If you start with 4 different random points, will you still get the same convergence and the same final 4 clusters?
If you start with 4 different random points, will you always end up with the exact same clusters? No, not necessarily. If you started with different ones, you might end up with a different organization of clusters. You will still end up at a point where you can't make a small change to iteratively improve on it. You'll still eventually reach some point of convergence where we can't make changes. But there's not necessarily a guarantee that you'll always find the exact same clusters. Maybe you'll find something different, but that also might be useful to you for performing analysis. So there are different ways of potentially clustering, and there's no one result that is necessarily the correct answer to the problem. We're trying to group the points into similar points that we think might be useful for doing some analysis. You imagine that if you were running a news site and you wanted to group a whole bunch of news articles together, you might try and find related parts of news articles that are similar to each other, figure out groups of them, and use that to do some analysis on which users tend to be reading which articles or which articles are becoming more popular and that type of thing. And so there are different potential applications for what you could do with those clusters too. Now, I've been doing all of this in 2 dimensions, essentially, like an x-axis and a y-axis. But we've talked about the dimensionality of data a few times now, that right now I've been assuming all points are like 2 coordinates, like an x-coordinate and a y-coordinate. But in reality, our data might not have just 2 values that we're going to plot in 2-dimensional space. It might have many more values that we want to plot in space as well. So instead of 2-dimensional data, you might imagine that we could have 10-dimensional data. If every point of data had 10 pieces of information associated with it, that could be the data that we're trying to represent. And computers are actually pretty good at dealing with higher dimensions, even though we, as humans, struggle to conceptually understand what does it mean for something to live in 10-dimensional space. A computer can do the k-means math on 10 dimensions really no differently than it was doing it for 2 or 3 dimensions, for example. But there do still become some problems that happen as we increase the dimensionality of the data. First, it's going to take longer to process. The more different dimensions you have more information that's potentially out there. But also, that data might be a little bit messier, that as we add more and more dimensions, the clusters might not be as clear, as data might be really spread out across high-dimensional space. And so as the number of dimensions increases, even though computers can do the math, sometimes it's not as helpful to try and analyze things across so many dimensions, and sometimes it's easier to try and analyze things when there are fewer dimensions. And so one common area of trying to perform data analysis, especially when there are many dimensions, is to figure out how do you take data that has a lot of different dimensions, a lot of different values, and reduce the number of dimensions that are there. Like ideally, 10 dimensions feels like it's kind of hard to deal with. It might be easier if we could take that 10-dimensional data and just turn it into 3-dimensional data. That might make it easier to analyze. We might be able to find clearer clusters because the points are just less spread out across all these different dimensions. And so it might be nice if we could figure out some way to turn high-dimensional data into low-dimensional data, just to make it a little bit easier for us to analyze. And so this is an area of data analysis known as dimensionality reduction, where you have data in many, many dimensions, and you'd like to shrink it down into fewer dimensions. And there are lots of reasons you might do this. One reason is maybe you want to then use that lower dimensional data to do some clustering or other kinds of data analysis. But there are lots of reasons why you might want to take data in many dimensions and figure out how to shrink it down. And so let's take a look at a simple example to try and understand some of the possible approaches to how we might engage in dimensionality reduction. I'm going to show you some 2-dimensional data, so data that has an x-coordinate and a y-coordinate. And we're going to think about how we might try and reduce that data from 2 dimensions to 1 dimension. And as we do this with 2 dimensions and 1 dimension, you can imagine how you might try and do this in higher dimensions too. But here's 4 data points that exist in 2 dimensions. Each one has an x-coordinate, meaning how far to the left or to the right is that point. And each point also has a y-dimension, meaning how far up or down is that point. And what I'd like to do is, instead of plotting these points in 2 dimensions, I'd like to plot them in 1 dimension, meaning they're just along a single line. And how could I do that? Well, what lines do I have here? Well, one line I have is this y-axis here, this vertical line here. And so if I wanted to convert these 2-dimensional points to 1 dimension, what I could try to do is project the data from a higher dimensional space onto a lower dimensional space. So what do I mean by that? Well, what I mean is right now these points live in 2 dimensions. And if I wanted to project them onto this single dimension, get them to work in just 1 dimension instead of 2, I'm going to map each of those points onto this line, this axis line here. And this is what the data ends up looking like. And that technically works, but we've lost a lot of information here. One thing you might have noticed is as we moved from the higher dimension to this single dimension here, all of the points, they look pretty close to each other right now. They're pretty bunched up together, whereas originally, that data was pretty spread out. There was a lot of variance in that data that represented differences between the data points. But when we mapped all of those data points onto this one line here, we lost a lot of that information. So that wasn't a great way to do the dimensionality reduction, because even though it worked, I lost a lot of the information. I lost a lot of the variance. So how else might I do this? Well, instead of mapping everything to this vertical line here, what would happen if I instead tried to convert things from 2 dimensions to 1 dimension by projecting or mapping things onto this horizontal x-axis instead? That might make more sense, because if you look at my data, it doesn't vary a lot in the vertical direction. Up and down, these are all pretty close together. But left and right along the x-axis, they actually vary quite a lot more. And so by mapping things onto this axis, we actually preserve a lot more of that variance. You can still see how these data points are different to each other in a way that was much harder to do when we were mapping it onto that vertical axis. And so that's going to be one of the themes of dimensionality reduction. As we take things from many dimensions and map them onto fewer dimensions, we're going to lose some information, of course. As you take things from 10 dimensions and turn it into 3 dimensions, we're going to lose some information there. But ideally, we'd like to preserve as much of the information as we can, preserve as much of the variance between different pieces of data as possible. Let's take a look at one more example of some points and how we might try and go about dimensionality reduction. Instead of these 4 points, let me show you 4 new points. Here are the 4 points. And now let's imagine I, again, want to take these points, which live in a 2-dimensional space, and convert them into a 1-dimensional space so that they're a little bit easier to analyze. Well, I could try the 2 axes that I used before. I could see what happens if I try and project everything onto this vertical y-axis here. And we'll just project everything onto that line. And you'll see that that certainly works. There's some variance here. But we've definitely lost some information, too, that these 2 points look very close to each other. They look like they're very similar pieces of data, even though originally they were actually pretty different. So we could say, all right, well, instead of projecting them onto this vertical line, what if we instead projected them onto this horizontal line? We'll try that. See what happens. And again, that works too. There's definitely some variance here, although we've also lost a fair bit of information again as well, that now these 2 points, they look very similar to each other. They look like they're very similar data points, even though originally they were actually fairly different. They were fairly far away from each other. But we don't need to limit ourselves to just mapping things onto the existing axes of our graph. If we're converting things into 1 dimension, in other words, converting things just into being mapped along a single line, we could map it onto any line that we could draw through this space. So I could draw a different line. For example, maybe I'll draw this line instead. And now, if I take all the points and just map them to where on the line are they closest to, now I have all of this data that's now been converted into just 1 dimension. I can define each of these points just by defining where it appears along this line. But I've managed to capture a lot more of that variance, that the points didn't have to move as far. I'm still able to capture a lot of the difference in the data between the points and the information that I had in the original data set. So there are a bunch of different strategies. This one is a variant on an idea called principal component analysis, but we'll look at some other strategies later in the course too, that allow me to take data in many dimensions and figure out how to reduce it, get it into smaller dimensions, so that I can then use it in an algorithm like k-means clustering to be able to potentially cluster data a little bit more easily. There are some other limitations to k-means clustering too, though, some challenges that we're going to have to think about as we're figuring out how we're going to go about clustering data. And that pertains to what the shape of the clusters looks like. Remember that k-means clustering, the means part of that, means that each cluster is really defined by the average position of all of the points in that cluster, the middle of where that cluster is. And you can think of that as kind of defining a circle, and each cluster is kind of circular shaped in terms of all of the points that are kind of close to wherever the center of that cluster is. But not all clusters are going to be perfectly circular shaped in that sense. For example, let's take a look at this data set here. Here we have a bunch of data. And it might not be obvious how many clusters there are, but if I had to say how many clusters there are, I'd probably say that there are really 2 different groups of points that seem to be going on here. We have this group of points here in the middle, and then there's definitely a gap around the middle. And then there's all these points around the edge, this kind of circular area that seems to be forming a different cluster of its own. Now, do we think that k-means clustering will be able to figure out those 2 clusters? Well, let's give it a try. We'll go ahead and start with 2 random cluster centroids. We have our red cluster centroid here and our blue cluster centroid down there. Again, these positions were just chosen randomly initially, but we'll iteratively improve on them over time. And we'll assign every point to which of the 2 they're closest to. So right now, this is the red cluster up here, and that's the blue cluster down there. We'll go ahead and follow the algorithm that we've seen run a couple of times now. We'll take each of the cluster centroids and move it to the middle, or the average of all of the points that are currently in that group. So red is going to move and blue is going to move. And then we'll reassign some points. So these points are now closer to blue. We'll update the cluster centroids. These points are now closer to blue. We'll update again. And we can watch and see as we update again and again. We're making small changes, changing just a few data points in terms of which cluster they happen to belong to. And at the end of it, we've updated the clusters. And once we don't have any more that we need to update, we'll have found our 2 clusters. And this is what k-means clustering decided were the 2 clusters in the data set. We found a red cluster center here, and all of these points are closest to red. And we found a blue cluster center here, and all of these points are closest to blue. And That could be a reasonable clustering. Maybe that's useful to you to understand which points of data fall on this side and which points of data fall on that side. But in this case, again, it didn't quite match our intuition, that what we might have wanted for the algorithm to find was that there was a middle cluster here of all the center points, and then a cluster for all of the points around the edge as well. And so k-means is going to struggle with that kind of clustering, because k-means defines a cluster by what the center of the cluster is. And if you think about what is the center of this middle cluster, well, it's probably like the middle of this little blob here. And what is the center of this outer ring? Well, the outer ring is kind of a circle, so the center is also going to be kind of in the middle here too. So this k-means approach might not be so good for this particular data set. But it turns out there are a variety of different ways that we can cluster, a number of different algorithms that we could use for figuring out how we're going to take data and organize it into different clusters. So let's take a look at one more clustering algorithm, just so we can understand some of the alternatives. So what are some other ways we could go about clustering this data? And the alternative we're going to look at is an algorithm called dbScan. So dbScan is a density-based algorithm for trying to figure out what the clusters are. And what do we mean by density-based? Well, density is all about how closely packed together particular points of data are. And the idea behind dbScan is to say that if there are a bunch of points that are closely packed together, that are densely packed together, well, then odds are those should form a cluster together. That if we have a bunch of points that are near each other, those are going to be the ones that form a cluster, and that's how we'll try to define it. So how could we go about doing this? Well, the first thing that dbScan needs is we need to define what it means for a point to be in kind of a dense area. And we're going to define that by defining a particular kind of point that dbScan calls a core point. And a core point is some point of data in this data set that has at least a certain number of other points that are close to it. And we get to define what we mean by close to it, and we get to define how many neighbors it has to be close. But for example, let's take this point here, this red point here. That one seems to have a bunch of points that are close to it. So we would define a particular distance that we're going to look, like within a certain radius of that point. And we would define a certain number of neighbors that it needs in that radius to be considered a core point. And in this case, if I want to call this a core point, maybe I'll pick something like 5 points. There need to be 5 points in this circle in order for the point to be considered a core point. If you got 5 points within this distance, then this seems to be kind of a dense area. We'll call that a core area. So this becomes a core point. Conversely, if you look at this point over here and look at that same radius, how many points are in that neighborhood, we don't have 5 points here. We only have 4 in this case. And so that's not going to be a core point. We won't call this a core point because it doesn't seem to be in a dense area. It doesn't have a lot of neighbors that are close to it. And so how does dbScan work? Well, what dbScan is going to do is it's going to start with a point, and it's going to check to see if it's a core point. So we start here. We could start with any point. But we're saying, is this a core point? Do we have 5 points in its neighborhood? We do. So we're going to call this a core point, and we'll give it a color, red, meaning it belongs to the red cluster. And then any of the other points that are in that circle, we'll go ahead and assign to that same cluster. So all of these other points in that circle, those are going to be considered red as well. And so now we have the start of what's going to be the red cluster. And now we're going to take a look at some other point. We'll take a look at this point, for example, and we'll say, is that also a core point? Does it have, in this case, 5 points in the circle of neighbors that are close to it? And in this case, it doesn't. We don't have 5 points here. And so we're just going to move on. If it's not a core point, if it's not in a dense area, we're going to ignore it and move on to another point that maybe will be. And so let's take a look at this point now. This one definitely does have 5 points that are in its neighborhood, that are in its radius. Some of them already belong to the red cluster. But for any of the ones that don't, we'll go ahead and assign them to the red cluster. Because this is a dense area, this point that we were looking at is red, belongs to the red cluster. And so all of the other points that are neighbors of it, those are going to be red as well. And this algorithm then is going to repeat. For any point that is surrounded by other points that are in a dense enough area, we'll go ahead and assign them to the same cluster. And by the end of it, this point might add these to the red clusters, which might add these to the red cluster, which might add these to the red cluster, so on and so forth, until we end up deciding and finding that we found this red cluster that ends up being this entire ring, because it's all just these densely connected areas that happen to be connected together. But we're not going to include these points in the middle because they're not close enough to any of these points that were along this outer edge. So we found one cluster, and then we can repeat the process with any points that we haven't already assigned to a cluster. We might say that over here, this definitely has 5 points within its nearby vicinity. So we can call that point a core point, color it in as blue, along with any of the other points that are inside of that circle, and repeat that process, and pretty quickly we'll end up getting a second cluster here as well. And so by using this density-based approach, a different approach to k-means, we've ended up finding different clusters, and in this case, they a little bit more closely match what we might have expected, where we have one cluster over here in the middle, and then one cluster along the outside. Now, it's also possible, as we go about running this algorithm, that there might be some points that are not close to any of the other clusters, that are not close to any of the core points. For example, this point way out here, is there a core point that would have colored in that cluster as belonging to either the red or the blue cluster? Well, if you look at what's within a nearby neighborhood of it, it's only this point, which we decided wasn't a core point. And so in that case, we might end up just calling that point an outlier, just noise, not belonging to any cluster at all. And that can be a useful thing to understand too. One other area of unsupervised machine learning and data analysis that we might be interested in is this idea of anomaly detection. If you have a whole bunch of data, you might be interested in understanding what pieces of data don't look anything like the other pieces of data. They're outliers in a sense, or they might be a little bit different. If you have data about a whole bunch of users, you might care about knowing which users are the anomalies or doing something unusual or unexpected. Or if you've got a bunch of transactions and you're trying to understand these financial transactions and look for ones that might be suspicious, maybe you want to be on the lookout for anomalies. Or if you run a website and you've got network activity logs and you're trying to look at those logs and understand and look for unusual or potentially suspicious network activity, looking for anomalies can be a helpful way to do that. And again, there are a number of ways that you might go about trying to look for anomalies. You could do it using this kind of dbScan approach. You could also try using some of the other algorithms we've used before. We talked about how you could use the nearest neighbor algorithm to look for points that are close to the point that you're interested in. Maybe if the points that are close to the point you're interested in are kind of far away, then maybe you could start to think of that point as an anomaly if there's nothing that happens to be close to it. Yeah, question?
Is clustering limited to numerical data that you can plot on a graph, or can it be used to detect similar colors or other inputs?
Yeah, could we use this on things that are not numerical, something like color or other types of inputs? Ultimately, a lot of the algorithms we're looking at here do rely on us having numbers to be able to take some idea and put them to numbers. But even if we had a different concept, something like text or colors or other types of data, we can often find ways of taking that data and transforming it into a numerical form so that it's easier for computers to then work with and apply these kinds of algorithms. We've seen some of that already in the course. Remember when we looked at minimax for game playing, we looked at taking the idea of a game and putting numbers to the outcome of the game so the computer can reason about it more easily. And it'll be a theme we come back to throughout the course as we look at different ways we can try and take information and map it into numbers so that we can solve problems like clustering or like anomaly detection as well. So this idea, clustering, anomaly detection, these are some of the things that we can do with unsupervised machine learning, just taking some data and trying to do some analysis on it. But what else can we do? What other problems might we try to solve? Well, one problem we might try to solve is to try and learn some association rules. So what are association rules? Association rules are all about having some data, and it's unlabeled data, it's unorganized data, and we're just trying to understand patterns and relationships between those variables, how those variables might relate to each other. And I'll give you an example where association rules are quite common. They're quite common for something called market basket analysis, understanding what kinds of things people are purchasing at a store. So imagine that I run a grocery store, and I have here a grocery cart with a few grocery items. And you might imagine, what might I care about knowing in terms of what people are buying at the grocery store? Well, I have a bunch of data. And the data I have is data about what people came to the store, what they ended up buying, and what they bought together. So for example, I might know that for one particular person who was a customer at my store yesterday, they bought broccoli and they also bought bananas. But I might be interested in understanding if there are relationships between those particular variables. That if I buy a banana, am I more likely to buy a broccoli? Or if I buy a banana, am I more likely to buy carrots, for example? What is the relationship between items that are in the store and the way people are interacting with them? And that might affect the kind of discounts that I offer, or where I place items in the store, or how I choose to price particular items in order to figure out what the relationship is between all of these items. And I might be interested in not just relationships between one item and one other item, but maybe a set of items and another item. For example, if someone buys flour and sugar, maybe they're more likely to buy eggs. And so I want to know for this particular set of items, or an item set, as we'll come to call it, what relationship does that have on some other variable that we might be interested in measuring? So let's take a look at some data and see how we might engage in a little bit of market basket analysis to take this data and try and understand it. So I have here a whole bunch of shopping carts representing different customers that are coming to my store, for example. And imagine that one of my customers bought these items. They bought item number 1, item 2, item 3, item 4. Each one of these numbers just represents something that might have been in this particular customer's cart. So maybe they're different kinds of fruit or milk or other vegetables or something else that they're buying at my store. And that's going to be true for all of these customers. So for the other customers too, we'll take a look and see what's in their basket. We have 1, 4, 5, and 6. We have 1, 3, 4, and 7. Each one of these numbers just corresponds with some item. This person bought items 3, 4, 7, and 8. That person bought items 1, 3, 5, and 9. So I have a bunch of data here. It's just data about each person and what they happen to buy. What kind of analysis could I do here? Well, one simple thing I might analyze is the support. What is the support? The support is a measure of how frequently a set of items appears in a data set. So here's my data. And let me say, what if I wanted to know the support of item number 1? How often do people buy item number 1? Well, I could look at these 5 baskets and say, how often do my customers buy item number 1? And that seems to happen in these cases. So of my 5 customers here, I have 4 of them who have bought item number 1. And so the support of item number 1 is 4 over 5. There are 4 people that bought item number 1. I'm looking at 5 pieces of data. So it's 4 over 5, or 80%, or 0.8, we might say, as the support of item number 1. What is the support of item number 8, for example? Well, for item number 8, that one only appears one time. There's only one customer who bought item number 8. And so that one has a support of 1 over 5, or 0.2, for example. But you don't just have to calculate support on individual items. We can also look at groups of items, too. So if, for example, I were to say the item set 3, 4, and 7, how many people in my data set bought all 3 of those items together, item number 3 and item number 4 and item number 7? Well, in this case, if we look at the data, it turns out it shows up twice, that there are 2 people that bought items 3, 4, and 7. So that has a support of 2 over 5, or 0.4. So for any item or any item set, we can define the support for how often does that appear in the basket. And that can help us to learn rules, that these things seem to be often bought together. And once I ask you, like, how many times are 3, 4, and 7 bought together, it's pretty easy to find. You just look at all of the transactions. You find how many of them have 3, 4, and 7. But the tricky part is often identifying those particular sets in the first place. Because right now, with only a few items, it's not too difficult. But if you imagine a grocery store that has not just a few items, but 1,000 items, how many ways are there to define a set of 2 items out of 1,000? It's something like 500,000 different ways. And how many ways are there to define sets of 3 items out of 1,000 items? That's going to be more than like 100 million different ways for how you can define those sets. So again, the challenge is, even though we could try and brute force it, there are just so many possibilities to go through. What we'd like is some efficient way to be able to take this data and figure out what are the popular, the frequent item sets, the ones that people are often buying together. Take a short break here, and then I'll pick up from the end of that section. right? So what we'd like to do now is find an algorithm that will allow us to efficiently determine what the frequent item sets are. So what is that algorithm, and what is it going to look like? The algorithm we're going to use is called the a priori algorithm. And what it's going to do is it's going to take our data. That's just a bunch of different transactions of what people had in their shopping cart, what items they purchased. And it's going to identify for us what the frequent item sets are. And importantly, it's going to try to do so efficiently, rather than consider all of the possible ways there are to group together 3 items out of all of the items you're selling in your store. It's going to efficiently look for which are the 3 items that are going to be sets that are going to be pretty frequent. And here's how we'll do that. We're going to start by looking at small item sets, just sets of 1 item at a time. And we'll use that to combine them into larger and larger sets that we're interested in. So let's walk our way through the algorithm. In this case, we have 9 items that we're interested in evaluating. And so there are 9 items in our store. In practice, this could be thousands of items, but we'll keep it simple for now. And then let me show you again the data we were looking at before. This is the same data as before. I just have 5 different people, and I have the items that those people bought. So one person bought items 1, 2, 3, and 4. This person bought items 1, 4, 5, and 6. This person bought items 1, 3, 4, and 7, and so forth. And what the algorithm is going to do is first take each of these sets of 1 item, just individual items, and calculate the support. In other words, how many people bought item number 1? How many people bought item number 2? And if we calculate the supports, here's what we get. We get 0.8 for item number 1, because if we look at the data, there are 4 people that bought item number 1, so 4 out of 5, that's 0.8. What's the support of item number 2? Well, if you look at the data, there's only 1 person who bought item number 2, and so that's going to have a support of 1 over 5, or 0.2. And we do the math for all of the other individual items, and we can calculate what the support is for each one of the items that are in our store. And so now what we'd like to do is start to form larger groups. We're interested in not just individual items, but groups of items that are often bought together. But first we can say we want to ignore anything that's not frequent. What we're looking for here are frequent item sets that show up a lot in our data set. And so we, the people defining this algorithm, we need to decide what does it mean for something to be frequent. And in this case, with only 5 people in my data set, I'm going to say that in order for it to be frequent, it needs to have a support of at least, let's say, 0.4, meaning it needs to show up in at least 2 out of these 5 people in order for me to consider it frequent. Of course, in practice, you're going to have many more than 5 people in your data set, and you could define a different definition for what counts as frequent. But in this case, we're going to say 0.4. That's our threshold for what it means to be frequent. And so anything that's not frequent, we can eliminate. Anything that has a support of 0.2 in any of these cases, those are definitely not going to be frequent. And so we'll go ahead and just eliminate them. And so we're left with all of the individual 1 item sets, in other words, sets of 1 item, that happen to be frequent, which in this case are 1, 3, 4, 5, and 7. Those are the items that show up at least 40% of the time in the data set that we're looking at. And so now what we're going to do is, instead of looking at sets of 1 item, we'll look at sets of 2 items. Now, how many ways are there to form sets of 2 items? Well, it turns out there are a lot of them. You could do 1 and 2, and 1 and 3, 1 and 4, 1 and 5, and so forth. And then you could do 2 and 3, 2 and 4, 2 and 5, and so forth. But the important thing now is that now that we've already eliminated some of these individual items, 2, 6, 8, and 9, we don't even have to consider those when we're looking at pairs. When we're looking at pairs, we can just focus on pairs of items that we know are already frequent, like 1 and 3 and 1 and 4, because something like 2 and 3, that's definitely not going to be a frequent pair, because if 2 by itself wasn't frequent, if we didn't have 40% of people buying item number 2, there's no way we're going to have 40% of people buying both items 2 and 3 together. So we can just focus on the frequent ones and figure out here are the pairs for those. We could do 1 and 3, 1 and 4, 1 and 5, 1 and 7. Then 3 and 4, 3 and 5, 3 and 7, 4 and 5, 4 and 7, and then 5 and 7. And you'll notice that items 2, 6, 8, and 9, they're nowhere to be found. They're not included here because they weren't frequent when we were considering just individual items of 1. And so we don't need to consider those pairs. We've really cut down on how many sets of 2 we actually need to consider. So at this point, we'll repeat the process. We'll say now we've got a whole bunch of sets of 2, and let's bring back our original data. Here's our original data again of our 5 customers and what items they bought. And we can say, all right, let's go ahead and calculate the support for each one of these pairs. So we'll calculate the support for each one of those pairs. And what that means is we're saying for items 1 and 3, how many customers bought items 1 and 3 together? Well, we have 1 over here. They bought 1 and 3. This person didn't. They bought 1 but not 3. This one did. We have 1 and 3 over there. This customer didn't buy item 1, but that customer over there did buy items 1 and 3. So we have 3 out of the 5 customers that bought these 2 items together. 3 out of 5, that's going to be 60%, or a support of 0.6. So again, we do that for each one of these pairs that we're considering. And at the end of it, we can apply our same rule. Anything that wasn't frequent, anything that didn't appear 40% of the time or more in this particular case, we can go ahead and eliminate. And so a bunch of these pairs we can eliminate. 1 and 7, that one only showed up 1 time. There was only 1 customer that bought item 1 and 7. That's not frequent. We can eliminate that. Same thing for the other pairs that didn't show up at least 40% of the time. And so now we can follow the same process. We started with groups of 1. Now we looked at sets of 2. Now we can say, let's start to form some sets of 3 by using this existing data. And so here are some sets of 3 that we could form using these numbers, 1, 3, 4, 5, and 7. But importantly, as with before, there are some of them that we can eliminate right away. In fact, we can eliminate all of these middle ones right away. And why can we do that? Well, why can we eliminate 1, 3, and 5 right away? Well, we can do that because one of the sets of 2 that's included within it, 3 and 5, that one we already decided wasn't frequent. 3 and 5 only shows up 20% of the time. So there's no way that if 3 and 5 wasn't frequent, there's no way 1, 3, and 5 can be frequent, because that could only be the same or fewer people that bought all 3 of those items together. Same thing here for 1, 3, and 7. We already know that 1 and 7 is not a frequent set of 2. And so if 1 and 7 is not a frequent set of 2, we can eliminate 1, 3, and 7 from consideration as well. And so by the end of it, there are only 2 sets of 3 that we really need to consider. We need to consider items 1, 3, and 4. And that's because all of the individual sets of 2, those are already frequent. 1 and 3, well, that one's frequent. It shows up this often. 3 and 4, that one's frequent as well. It's still highlighted here. And then 1 and 4, that one's also frequent. All the combinations of 2, those are frequent. So we'll consider 1, 3, and 4. And we'll also consider 3, 4, and 7. So even though from 9 items, there are quite a lot of ways of forming sets of 3, the a priori algorithm has helped us to quickly whittle down to just the 2 sets of 3 that we actually need to care about, 1, 3, and 4, and 3, 4, and 7. And we can do this again. We can say, all right, let's take those, calculate the support, and figure out how often do they show up. It turns out each one of these 2 shows up 40% of the time. They each show up twice. And so we can say, all right, well, given those sets of 3, let's try and form a set of 4. So how could we take these 2, combine them into a set of 4? Well, we could form 1, 3, 4, and 7. That's a set of 4. But is it going to be frequent? And I think we could safely say that it's not going to be frequent. Because if we know that 1, 4, and 7, that's not frequent, there's no way 1, 3, 4, and 7 is going to be frequent. And so this set of 4 we can safely ignore. It's not going to be a frequent item set. And so what we've done is identify some sets of items that are likely to occur together, 1, 3, and 4, 3, 4, and 7. And based on that, we can start to form some association rules. Rules for if you bought these items, are you going to buy that item? So for example, we might try and analyze this rule here, 3 and 4. If you bought these 2 items, how likely is it that you're also going to buy item number 7? What is the strength of that relationship between this item set here and that particular item over there? And how are we going to measure that? How do you measure the strength of the relationship between a set of items and one other item? So for example, what if I wanted to evaluate what is the relationship between buying carrots and bananas and buying grapes? Well, what I would do is I would look at all of the customers in my data set that bought carrots and bananas and say, of those customers, how many of them also bought grapes? And that would give me a sense for the strength of the relationship between one set of items and one other item that I might care about. And so let's take a look at this too. We're going to define this by defining what we call the confidence. The confidence is a measure of the strength of the association between sets of items. And so if I want to understand what is the confidence of buying items 3 and 4, predicting that you'll also buy item 7, let me first ask, well, which of these customers bought items 3 and 4 together? And we'll see that there's 3 of them, 3 and 4 here, 3 and 4 there, 3 and 4 over there. And of those 3 customers, how many of them also bought item number 7? Well, there's 2 of them. This customer here also bought item number 7. That customer there also bought item number 7. And so the confidence of this rule, how strong this association is, well, for 2 out of the 3 customers, they follow this rule. They bought 3 and 4, and then they also bought item number 7. And so that one we'll say has a confidence of 0.67, or about 2/3 or so. But we could try this for other orientations of this rule if I move things around. What about if we look at buying items 4 and 7 together, and how often that predicts that you'll buy item number 3, just rearranging these a little bit? Well, which of these customers bought items 4 and 7? That's these 2 over here. And of those customers, how many also bought item number 3? Well, they all did. Both of those customers also bought item number 3. So at least for now, this appears to be a pretty strong association rule. It has a confidence of 1, that everyone who bought items 4 and 7 is also buying item number 3. Now, of course, again, this is a pretty limited data set. I'm just looking at a couple of customers in terms of what they've had in their shopping cart, what they chose to buy. If you had much more data, you'd be able to do some better analysis here to really understand what is the relationship between these items. What is the relationship between different variables that happen to show up in your data set? So this can be a pretty powerful tool for doing something like that. We'll go ahead and put the shopping cart away, since we won't need that anymore, at least for now. So one final topic that I want to take a look at as we explore what it is that we can do with all of this data. Why might you care about understanding patterns and relationships between data and trying to group users into clusters? One popular application is the idea of recommender systems. And recommender systems show up all the time in software now, where computers are recommending music for you to listen to, or photos you might enjoy, friends you might want to follow, videos and movies that you might like. So let's take a look at some of the ways we might go about implementing a recommender system. So what is the idea? The idea is that let's imagine that you have watched a whole bunch of movies. You've watched these 5 movies on some movie streaming website, for example. And what we'd like for that website then to be able to do is recommend some movies for you to watch. Say that these are some movies we think you might enjoy. And ideally, try and do a pretty good job of doing that, of figuring out what are the other movies that you might enjoy from all of the movies you could potentially be watching. And odds are there's a big database of movies that we could be looking at. And there are a number of different approaches that we could take for figuring out how to do something like this, how to recommend what movies you might like. So let's look at a high level at a couple of those possibilities, different ways you might go about trying to make recommendations for what kind of movies you might enjoy. Well, first of all, we need to understand what is the data about a movie that we have access to. Ultimately, we need some data in order to make decisions, because without that data, we'd have no way of knowing what kind of movies you might or might not enjoy. So let's try and define some of the features of our data set. What are the features of each movie that we might care about measuring that would allow us to make some kind of a decision? And in this case, we could define some features like, what is the genre of the movie? What year was the movie published? Who are the director and the actors and the writers? Maybe you like a particular director, or you really like a particular actor. How long is the movie? Maybe you like shorter movies or longer movies. What was the budget of the movie? All of these things are things you might care about when trying to look at a movie and analyze what its core essence is, what are the features about it that you might care about, to understand how to make a recommendation. One more break, and then I'll wrap up this section. So now that we've defined all of these different features of movies that we might be interested in analyzing and understanding, we have a data set of a bunch of movies and values for each of those different features. What we might care about doing now is making some kind of recommendation of understanding, given this movie that you've never seen before, is it a movie you're going to like or not? So how could we go about doing this? There are a number of algorithms that we could use, but let's go back to an algorithm we looked at earlier in the course, the idea of nearest neighbor classification. With nearest neighbor classification, remember the idea was that if we had some data point and we wanted to classify it as belonging to one group or some other group, we'd plot it in space and figure out what other point is it closest to. So let's take a look at some example data. Let's imagine that there's a movie here that you've already watched, and let's say that at the end of the movie you rated that movie. You said thumbs up, you liked that movie. And let's imagine there's another movie that you didn't like. You gave it a thumbs down, you said you really didn't like that movie. And you could plot these in space based on the features that we've defined, based on features like what the genre of the movie was, or who the writer happens to be, or what year it was published in, for example. And so if you found another movie that you haven't seen yet, but it's pretty close to that movie you did like. And by pretty close, I mean it shares or is close to a lot of those same features. Maybe it has a similar genre or is written by similar people or the same people. You might say, do we think it's likely that you're going to like this movie or not? Maybe we say, yes, you probably will like this movie. And maybe we'll recommend it to you because it's similar to other movies that you've already liked based on the content of that movie, based on the attributes or features of that movie that we know that you've already liked. And so this kind of approach to recommender systems is one approach called content-based filtering. And the idea behind content-based filtering is that we filter through all of the movies you might be interested in by understanding what kind of movies or other types of items that you might be recommended, what kinds of things you enjoy. That if we know what kinds of movies you've already watched, we know what kinds of movies you already like, we look at the particular features of those movies and say, based on that, what other movies do we think are going to be similar to that, and therefore also going to be things that you're going to like as well. Now, there was a good question that was brought up earlier in this lecture about how you do this with data that isn't necessarily numerical, that not all data is going to be a number. Some things will be numbers. For example, you might imagine that the year of the film, the duration, and the budget, those are all numbers. You could put a number to what year it was published in or what the duration of the movie was in minutes, for example. And those are things you could imagine plotting in space and doing a nearest neighbor classification or some other type of algorithm using those numbers. But there's other information that maybe doesn't lend itself quite as nicely to being defined as just a number. For example, let's take the genre of the movie. How would you take the genre of a movie and put a number to that? Right? Some movies are action movies, and some are comedy, and some are romance or horror or sci-fi. How are you going to take that and turn it into a number? Well, we have a few different options. Here's one option. We could take all of the genres we're considering. Here's a bunch of different movie genres. And we could just assign a number to each one of them. We could say, all right, action is going to be number 1, and comedy is 2, and drama is 3. And therefore, you could say, if we already have a movie that you liked that had a genre of 1, meaning it was an action movie, then if there's another movie that also has a genre of 1, then maybe you're going to like that too, because it matches in terms of what the genre number is. But it turns out that this can be a bit of a problematic approach for a couple of reasons. But one problem is it's assuming that there's some kind of ordering to these genres that might not actually be true in reality. It assumes that if you really like action movies, then the algorithm might assume that, oh, you're going to like comedy movies more than sci-fi movies, because 2 is closer to 1 than 6 is. As soon as you have numbers in this kind of ordered range like this, 1 through 6, then if you try to do comparisons on distance, how far away is this movie from that movie, or that movie over there from this movie, well, then we're going to be assuming things about the relationships between those genres that might not actually be true. So instead of having one feature that's just a number that might end up being the result of some comparisons we don't intend, instead what we might do is separate this out into 6 different features, one for each one of the genres, where we have one feature that just describes is it an action movie or not, 1 or 0. So for an action movie, yes, it is an action movie. But for all of the others, no, it's not an action movie. And then have another feature for is it a comedy movie or not. 1 for yes, it is a comedy movie, and then 0 for all of the other movie genres too, and then the same for each of the other 4 genres that we have represented here. And as a result of that, we don't run the risk of thinking that a comedy movie is closer to action than a romance or sci-fi movie is, for example. And it also lets us do things like represent movies that might have more than one genre. Maybe we have an action sci-fi movie, and therefore we want to be able to represent both of those in our data set as well. So we can take data and figure out how to convert it into a form that we can then use for being able to do these kinds of comparisons by taking something like the genre and turning it into numbers. What about for text-based data? Sorry, forgot that slide was there. Let me go back a little bit and turn them into numbers, and then I'll walk and then make that an easy transition. OK, so we can take the genre and turn it into numbers. So this kind of approach, where instead of just using a single value representing the genre, like 1 for action and 2 for comedy and so forth, where we instead spread it out, is what's known as a one-hot encoding. You saw that before we just had this sequence of values where one of them was 1, meaning if there's a 1 here, that means it's an action movie. If there's a 1 there, that means it's a romance movie. If there's a 1 there, that means that it's a sci-fi movie. And that's a common way we try and encode features of data into our data set, by having a 1 if that thing is present and a 0 if it's not, kind of a binary yes or no, 1 or 0. Let's imagine now that we might have some other data, though, that's not just something like a category, like the genre of a movie. Maybe we also want to be able to draw inferences about a movie based on text-based data. Maybe we have a description of the movie. Here, for example, is a description of a movie. And I might be interested in understanding, based on the description of this movie, if you liked this movie, what other movies might you also like? And to be able to do that, it's important for me to figure out, like, what are the important words in this description? Because there are a lot of words here. I might be interested in understanding what are the important words. And what does it mean for a word to be important in the context of a piece of text? Well, one way you could define it is that the word shows up multiple times. That if a word only shows up 1 time in the text, maybe it's not so important. But if it shows up at least twice or 3 or 4 or more times, then maybe that means it is more important. So if I look at this movie description, what words show up more than once? What words show up at least twice? Well, one thing I might notice is the word magical. That shows up twice in this movie description. And so therefore, based on that, I might make the judgment that if you liked this movie, then if there are other movies that also have the word magical showing up in their description, maybe those will also be movies you'll like, because they might be about something similar. They share something similar in the description of the movie. But I do have to be a little bit careful, because there are also other words that show up multiple times. Words like the word she shows up 3 times here, or even more like the word the is going to show up a lot in any sequence of text for pretty much any movie description, or a or it, for example. There are a lot of words that just show up really frequently. So just measuring frequency alone usually isn't enough to really be able to tell whether a word is important in the context of a piece of text. So we need some other way. And often one adjustment we can make is, instead of just using the frequency of the word, we can use something called TF-IDF, or term frequency inverse document frequency. And what does that mean? It means in order to evaluate whether a word is important or not for a particular document, like a movie description, we look at 2 things. We look at, first, the term frequency, meaning how often does that word show up in the document. If the word magical shows up a bunch of times, it's likely to be more important. And then we also look at the inverse document frequency, meaning of all of the documents, of all of the movie descriptions, how many of them have that word. And if there are fewer of other movies that have that word, then odds are that word is a little bit more meaningful. It's a little more important. That if the word the, or the word she, or the word it shows up in a lot of different movie descriptions, then those words probably aren't so important for determining what's actually relevant in the description of a movie. But if the word magical doesn't really show up in that many descriptions, odds are that word is going to be a little bit more important. So using these kinds of ideas, we can develop a content-based filtering system, where we can say, if we know what kind of movies you like, then we can recommend another movie to you based on movies that might be similar to it. But there's another approach we can take too, which is something called collaborative filtering. So what is collaborative filtering? Collaborative filtering is all about the idea of not just learning about what movies you like and learning what movies are similar to it, but learning from a bunch of different people. That if we know what kind of people are similar to you, then maybe we can recommend movies that those people liked, and those might be ones that you might enjoy as well. I'll take a break, and then I'll pick up from there. So what is the idea behind collaborative filtering? The idea is, instead of saying what movies are most similar to movies you like, the idea instead is to say what people are most similar to you, what people like the movies that you've liked or watch the movies that you've watched. And then using that, we can draw some conclusions about what movies you might also like. So let's take a look at an example. Let's imagine that we have 5 movies of interest that we're considering inside of our database. And let's say that you have watched and liked these 2. You've watched movie number 1 here, and you've watched movie number 3. Then we'll compare that to what other users in the database have also watched and liked. Maybe there's a user here that's watched and liked these 3 movies. And then we have a user over here that's watched and liked movie number 1, and movie number 3, and movie number 5 to you. The basic idea behind collaborative-based filtering is to say, let's look for users that are kind of like you. That if you like this movie and you also liked this movie, if this person over here also liked this movie that you liked, and also liked this other movie you liked, well then here's a movie that you haven't seen yet, but we know that someone like you also watched and liked that movie, and therefore that movie might be one that we recommend to you as well, as something that you potentially might like too. And the more data you have, of course, about other different kinds of users, the better you can make those kinds of judgments. And so if, for example, you have a whole bunch of people that you've mapped out based on what kind of movies they tend to like, well, then if you come along and you want to say, are you going to like this particular movie? We are asking, is this a movie that we might want to recommend to you, the user? Well, what we can say is we can say, look at the users that are near to you. Again, we could use a nearest neighbor-like approach here to be able to say, what are the users that are similar to you within a certain distance from you based on however we've chosen to define the properties of who a user is and what they like. And we might look at, say, how they rated that movie out of 5 stars. And so if there's a movie you're interested in, we'll look at the people that are close to you, that are near to you, and what did they rate it? One person maybe gave it 4 stars, one person gave it 5 stars. And so if the people near to you happen to like that movie, then maybe that's one that we'll recommend to you as well. And so, of course, the more data that an organization has about you and other users, the better it's going to be able to make those kinds of predictions. And that's one of the reasons why organizations are so interested in trying to collect as much data on their users as possible, because the more data they have, the better they're able to make these kinds of prediction models, to be able to analyze that data, understand the patterns, and figure out information about you, not only to recommend movies or other things to you, but also to recommend things to people that are similar to you, that have similar interests, that have watched or experienced similar kinds of things. And so just always good to be mindful about ways in which organizations might be collecting your data and might be using that data, because increasingly data is being collected, being used to train these kinds of machine learning models, and therefore being used to make decisions, make recommendations to you or to other people based on your activity, the things you've watched, the things you've seen, the things you've clicked on, how long you spent watching a particular video, and so forth. And how can an organization test something like this? How could they know if they've built a recommendation system, is it any good? Or if they have 2 different approaches of what they want to recommend, how do they know which one is better? One way they can do it is just by testing it on users, using something known as A/B testing. That if I have one recommendation algorithm and I have another one, and I want to try them out, well, maybe I'll use recommendation algorithm number 1 on this group of users over here, and recommendation algorithm number 2 on some different group of users, and I'll just evaluate, see which one performs better by trying these recommendations and seeing which one results in more people clicking on the video, or watching the movie, or watching more of the movie, for example. All of those are metrics that they can use in order to test these kinds of algorithms to really see what it is that they can do with it. So in the end, there are a lot of different ways that we can take data and figure out how to analyze it. We can try and cluster it into different groups. We can try and understand the relationship between different variables. We can try and use all of that data, not only from you, but also from other users, to try and make recommendations to you or to other people too. So a lot that we can see that computers can do with data and a little bit of algorithms. And we're going to continue to see more as we explore this course and try and understand more about machine learning and artificial intelligence. So we'll see you next time.